Thanks to the organizers for giving me this opportunity to talk about my work. I'm a PhD student at IISc and Raman Research Institute. I will be talking about peculiar velocity correction in cosmological inference from supernovae data. So you know that our universe is very well described by this 6-parameter lambda CDM model with the underlying theory of gravity as the general relativity and the energy content of the universe distributed among dark matter, dark energy, and the ordinary baryonic matter. Further, with the assumption of homogeneity and isotropy, the space-time of the universe is described by this FLRW metric, where AT is the scale factor and its logarithmic derivative is the Hubble parameter. So we have 6 free parameters. In order to constrain all of these parameters, we need to have information about the evolution of background as well as perturbation in the universe. However, some of these parameters can also be constrained using background data only. So the supernova data is among the best probe for this background expansion. In the supernova data, we have magnitude and the redshift. So magnitude is computed from the observed flux and redshift from the spectral analysis. So this is what we have in the data. Now, these magnitude and redshift are related by this expression. So theoretically, we can compute magnitude at a given redshift by this relation, where dl is the luminosity distance, which depends on the redshift, and that is given by a given cosmology. So given a cosmology, we have different parameters. Depending on the value of these parameters, we will get this m, and we can compare the cosmological model with this data and constrain these parameters. However, the presence of peculiar velocity affects the inference of these cosmological parameters. So peculiar velocity is the velocity of galaxy or any object relative to the Hubble flow. So suppose this is the Milky Way galaxy, and we are targeting at some supernova residing in this galaxy. Then this galaxy has a velocity, a recession velocity, due to which it is going out from us, that is due to Hubble flow. But in addition to this Hubble flow, it can also have some velocity called peculiar velocity due to the attraction of some other galaxies. Further, so if this is the case, then the total observed velocity will be different from the cosmological expansion. So this can arise from, this peculiar velocity can arise from different sources, like due to our motion relative to the cosmic rest frame, or due to the motion of the galaxy inside the galaxy cluster, or due to the motion of the whole cluster towards some bigger structure. So if this is the case, if there is some peculiar velocity, then our observed redshift will have contribution from cosmological as well as this peculiar motion. And in observation, we cannot disentangle these two effects. And what enters in this expression for this magnitude is only the cosmological expansion. So if we use this observed redshift and we do not take this into account, then it will bias our result. So in this case, we see that we have now errors in 2 variables. We can treat this as errors. We have errors in both variables, redshift as well as in the magnitude. So we can treat this as an errors in variables model. So errors in variables models are just model fitting problems with errors in both dependent and independent variables, something like this. In such cases, even for a very simple linear model, there is no analytic solution. And for non-linear model, it is not obvious how to write the merit function. For simple cases of non-linear models, when the model is smooth, continuous, and differentiable function of its parameters, we can invert that function and we can write the likelihood. But in general, there is no method for fitting such such models with errors in both variables. So our approach, so first we define our approach, we come with an approach to consider this errors in variables problem, then we apply it to cosmology. So suppose this is our model, y as a function of theta and x, where x is independent variable, theta is the cosmological parameters or any parameters, model parameter. In that case, this is how we write the usual likelihood. But if we have errors in both variables, what we do, we treat the independent variables also as parameter. So we replace this x by x star. Now x star is a parameter, and theta is the model parameters plus this independent variable parameter x star. Now the total number of parameters become more than the total number of data points. So in order to avoid possible model fitting, we include this regularization factor p chi square, which is given by this expression. So this is the expression for chi square distribution in chi y square. And this chi y square, the general chi y square is given by this expression. Here px, this is prior on x star, and p theta is prior on the model parameters. Now, based on that, we write this is the likelihood. So, I have just taken the log of that expression for the redshift magnitude relation, and this is the regularization term. When we take log, this is what we get, and this is the usual chi-square term. We also, to compare with other estimators like even, which is the general estimator for model fitting, which does not take into account the z error or the redshift error of peculiar velocity. And this is another case when it takes into account the peculiar velocity, but only for the linear approximation of the model. So, we linearize this model redshift magnitude relation, and then we use this method. So, now this is the result for the 3 different cases. For even E2 and E3 shown in different colors, we see that we get a slight shift in the central value of the parameters, inferred cosmological parameters, omega matter and H naught. And this is a table showing the same value. So, in even case, when we completely ignore the effect of peculiar velocity, we get 0.28 and we get 0.30 in case of our estimator, and this is in between, that is the linear approximation. And this is for the Pantheon data and the lambda CDA model. The interesting thing is there is no model or measurement of peculiar velocity involved. So, there is a background model for the cosmology, but no model for the evaluation of peculiar velocity. So, we see that there is a few % shift in the central value, but still all these values are consistent with each other. Now, we applied it to the simulated data with different sigma m. So, at present, this is the value of sigma m, that the uncertainty in the magnitude in this supernova data. Now, we take a smaller value with more precise data, we see that there is more significant deviation in these. So, we expect that in future we will be able to distinguish or to capture this effect of peculiar velocity in cosmological inference. So, this is the summary slide. The effect of unaccounted for peculiar motion is to shift the estimate of cosmological parameters, and to take this into account, we consider cosmological model fitting as an errors in variable problem, and for this problem we treat the independent variable as parameters, and with Pantheon data we see a few % shift in the cosmological parameter. And it also allows us to estimate the peculiar velocity of individual galaxies. So, currently we are working on it, and up to a lower rate, depending on the precision of the data, at lower redshift we can actually estimate this peculiar velocity of individual galaxy. Thank you.
Okay, thank you, Ujjwal, for a nice talk. Rishi, maybe.
Yeah, so you chose one regularization scheme
Yes.
to avoid overfitting.
Yes.
But so is your result sensitive to what kind of regularization scheme you choose, or is this the only regularization possible, or other regularizations are possible, and will the results change if you choose something different?
Okay. So, you can take other regularization also, and okay, so this is one choice of regularization. We can also take other regularization. The simplest should be, so the role of this regularization is to impose a chi-square distribution on this chi-y square. Now, we can just take this chi-square, we can impose that chi-square per degree of freedom remains close to 1. That would be even simpler case. And the effect, so we can take different kind of this regularization term. The effect of this is to keep chi-square closer to 1, but it does not affect the result very much. But yes, it shifts to slightly better fit.
So here this chi y is a free parameter?
Chi y square is given by this expression, just yi minus f theta.
Okay. And the k is a free parameter?
K is the number of degrees of freedom. So, in this case, I have taken this total number of supernova minus number of model parameters theta.
Yes.
Can you explain what do you do with the error bars on Z? There will be error bars associated with redshift also.
Yes. So, in case of this peculiar velocity, we do not have error bars in Z because the spectroscopic measurement gives very small error, and but if we have some errors on redshift, this our method will take that into account already. It will go as in prior on theta on these redshift parameters.
Okay. Any other questions? So, how much is the improvement in error in adding peculiar velocity?
This chi-square you are asking. The improvement is around 0.05 or something. in chi-square. But that does not matter. Even if I do not include this, we'll get roughly the same result. But yes, it does move in. And it also depends on the precision of the data. So if you have better precision, it can improve it.
If you include the errors in redshift measurement as you were suggesting, do you expect an improvement in chi-square or what?
No, actually, if we include this, that will be basically restricting a prior that it is in this line. But we have, so I do not expect much change in the result.
You are forcing chi-square to be 1, right?
Yes, yes.
Right.
Uh,
That's
yeah.
what I expect. Okay.
So as long as the result is dominated by the data, the priors will not affect it.
Which part of the data is telling you about the peculiar velocity?
Actually, okay, so in the redshift range, you are saying.
So even if I give you a sample, how are you disentangling between the peculiar velocity component and the galaxy's true component? I mean, how do you must have an estimate, right? Which part of the information is telling you to distinguish that?
Okay, basically, okay, the information is coming from the model. So you are assuming a background cosmological model that is telling you what should be the value of correct redshift. So basically, so when you do not have redshift or errors, okay, then you can estimate these parameters H0 and all these. Okay, now you want to also estimate the redshift parameters. So that also can be done if you have very precise data. So in the magnitude error, you move in the up and down direction to fit it better. Now in the redshift error, you move in the horizontal direction. So that
Maybe
is,
my question is the following: that the peculiar velocity is so nonlinear, particularly in our local universe, it's very difficult to make it a cosmology model dependent statement. In fact, if you see the
cosmological model for peculiar velocity.
peculiar velocity.
Yes, exactly, and that is why our result is very interesting, because it does not assume any peculiar model for peculiar velocity. The evolution of peculiar velocity, it is coming from just the lambda CDM background model plus the supernova data.
I see. Thanks.